So let us resume our morning session. Our next speaker is Konstantin Khanin from the University of Toronto, and he's going to tell us about the asymptotic behavior of transport maps related to the random forest Burgers equation and KPZ problem.
All right, thank you very much, and thank you very much for inviting me to this very nice program. So the title is Randomness, Integrability, and Universality. And it was a lot of randomness and quite a few of talks about integrability. So far it was, I think, not so many about universality, so I'll be talking about universality in context of KPZ problem. But I will be taking kind of not traditional point of view. Maybe I would say a few words about KPZ and how people look at it. So KPZ, Parisi-Zhang phenomena happens in many, many settings, and it's amazingly universal behavior. The only thing which is needed for that is disorder and two-dimension, or 1 + 1 dimension. And if you have 1 + 1 dimension and disorder, then on a large scales and large times, you see KPZ phenomena. And originally it was studied by Parisi-Zhang in the context of interface growth, but then it appears in many, many problems. And I will take more geometrical view. And I think that when you take geometrical view, you see certain structures which you don't see when you just look at the interface. So basically, the way to look at the KPZ is the following, that if you have random metric on a plane, so kind of you have a plane and some landscape of hills and valleys, and which is homogeneous, spatially homogeneous, but maybe not very correlated in different parts, far away from each other. And then you take faraway points, and you want to study to look at the geodesics connecting these 2 points. And then you can ask 2 questions. You can ask what are the lengths of these geodesics, and that would be what is interface type of growth of interface, H function, or the action. Or you can look at the geometrical properties of this geodesic, how far it deviates from a straight line. And that's the point of view I'm going to take. And I will be more interested here in these geometrical properties and universality of these geometrical properties. Now, I will not be talking about random metrics. I will be talking about setting which is Hamilton-Jacobi equation or KPZ equation or related Burgers equation. So the equation will be, and that's equation which people normally write for interface. So it's a time derivative interface of function h plus space derivative square is equal to viscosity times Laplacian of h, but here it would be, I would be in dimension, special dimension 1, plus a random potential, time-dependent potential. That's how disorder comes to the system. Now, if this f omega xt is a white noise in space and time, then it's called KPZ equation. But phenomena we are looking will be for large scales in x and t, so it's not that much essential that it will be white in x. And being white in x creates a lot of difficulties. So let's think this, it can be fine to consider it white in t, but in x it is smooth realization, some random field which is smooth in x. So it's not white noise, but colored noise, right? And then, of course, there are related, this equation is directly related to, so I would call it Hamilton-Jacobi equation, but also can be KPZ in a particular case. And of course, there is a related equation for the velocity field, u, which will have form let me put Laplacian u, it's although in dimension 1, minus random force, and this random force is just minus spatial derivative of the random potential. That is Burger's equation for the velocity field. And U here is just a gradient, spatial gradient of H. So whatever I put this is just derivative with respect of X. Or you can even, in this case, you can write stochastic heat equation if you use Hopf-Kohl transformation and transform to linear equation, which is stochastic heat equation, which is equivalent, all these three equations are equivalent. So we are interested in large time behavior of this equation. And there are two cases. There is a positive viscosity case or zero viscosity case, and this is inviscid case. And KPZ phenomena covers both cases. But I will be mostly maybe speaking about inviscid case. It's just easier to visualize what's going on here. So if you want to solve this equation when nu is equal to 0, this equation doesn't have strong solution. It has only weak solution, but there is well-defined physical weak solution, which is obtained in a limit when viscosity tends to 0. So you take initial value problem, you solve it for positive viscosity, then you take viscosity to 0, you get specific weak solution, and for this equation and for that equation. For the Burger's equation, where you use velocity field, the solution would have jump discontinuities, shock waves, and for the H function, it would have just corner points, some kind of corner points, so it will not be differentiable, but it will be Lipschitz, right? So how you solve this equation when viscosity is equal to 0? There is variational principle. Principle which allow you not to take the limit when viscosity goes to 0, but immediately say what will be the solution. So this variational principle is up to Lax and Olenek originally. It's the following way of solving this equation for H. So if you start with initial data, which is just your solution at time 0, and you want to find solution at time t, at particular point, say y, what you're going to do, you want to consider all possible paths, gamma, going down in time from time t to 0, and then for particular path gamma, you calculate action of this path on time interval 0 t, and this will be integral of gamma square velocity of this path plus f gamma tau, which is this f d tau. You integrate this action from 0 to t, and you also add terminal payoff. So you add the value of h naught function at the end point. And that will be the action of your path, and then you have to take minimum of this action. So you take solution of at point y at time t will be infimum over all paths, and actually this infimum will be attained, so it will be minimum of this action of the path. And the path which realizes this minimum will denote gamma naught, gamma bar, and this is a minimizer. So path which realizes this minimum among all the possible paths. And so the path, the action of the path is a value of function h. The velocity of this path at this point is a solution to this equation u. So that's how it's solved for nu equal to 0. And as I said, we're not interested in Cauchy problem. We're interested when t goes to infinity. So yes. Yes. No, it pumps energy in the system because no, it will not accumulate because energy will be concentrated in shocks. So shocks create dissipation of energy, and that's why it will be equilibrium behavior even if you pump the energy into the system. No, it's in this particular case because, so first of all, even for the hydrodynamic equation, in the limit of nu goes to 0, there is a anomalous dissipation, but it's not here. Here, the situation is different. It's well known that shocks, there is a dissipation of energy through shocks formation. But I don't want to go into this now. Okay, Pash, let's discuss it later. All right, so I'm interested in a very large T. Now, you can go from 0 to large T, or what I'll do, I'll fix sub T, and we'll think that my initial condition giving to started at minus infinity, something very low below. That's more convenient in systems with random dynamics. So in this situation, what I'm going to, so my time now is 0, and I want to write minimizer starting at some very low minus T. So that's where my initial condition is giving. And so there is a theorem which says the following, and actually this theorem should be correct in any dimension, but it's proven it's not so easy to prove. In dimension 1 it's correct. It says the following, that there exist infinitely long minimizers. So actually what it means is that if you start in some minus T, you get some minimizer at point Y at time 0. And then if you go further below, then this path starts to stabilize. So it will just go to a limit. So for all these points, there are infinitely long minimizers going down in time up to time minus infinity. And that's the object which I want to look at. And the situation will be the following, that I will draw the picture how this will look, and then I will explain why it looks this way, maybe. So it would look the following way. So it's just path going down, and many, many paths starting nearby this point will just go closer to this path. And they will get exponentially close. But then they separate, and this path would go, say, along this corridor. Then they'll meet sometime, but much later. But then they separated for longer time here. And so it would be two scales here. What you'll see, it will be two scales. One scale is that paths tend to get exponentially close to each other. And another scale that they tend to be separated for giving time scale. So if you wait infinitely long time, any two paths will come closer. But for giving time scale minus T, you will see that there are separated kind of points where this path concentrated. And this separation will be algebraic in T. So the distance, and that's what is prediction of the KPZ theory, will be order T to the 2/3. And that will be typical separation between points of concentration of these minimizers. And that's one of the exponents of the KPZ problem. But what KPZ basically says, it's not just separation as T to the 3rd, but the point field which you obtain here will have universal statistical properties when you scale it by T to the 2/3. If you scale it by T to the 3rd, this point field of concentration of points will have density order 1, and it has limiting statistics. And this statistics is universal, supposed to be universal. It should not depend on the probability distribution of this disorder here. And that's the main problem of universality, to explain why this is universal, and then, of course, also why the actions of this optimal path are also having universal behavior when you look how they depend on starting point after rescaling. All right? So this picture will be essential for me. Now, let me explain why this is happening. So, by the way, what is the transport map I'm talking about? Transport map is taking point here and see what is the image of this point. So it's just for giving time minus T, I want to see what is the map from here to here, or vice versa. And let me first explain why you will have this, you'll see this phenomena that things are concentrated with exponential scale. And then we'll discuss why they are separated by algebraic tail here. All right. So basically, you can think about this long dynamics transport map as a combination of many transport maps going for time interval, say 1. So there is a transport map here, and so on and so forth. Now, these transport maps depend on the realization of your disorder. So they are random maps. And you are taking iteration of these random maps. Now, how individual map look like? Well, it's a time one. So basically, individual map gi on x would look like x plus displacement order 1. Right? Let me call this map maybe fi, and displacement will be gi on x. I is a time, 0 to -1, -1 to -2, and so on and so forth. So I is equal to -1, -2, and so forth. So it's time one map, and this thing is random. Now, it's not independent for different I. It's not independent in KPZ problem. In principle, you can consider, of course, these sequences of maps and iterate them, but they're independent from each other. And I would say a few words about this as well. But here they're dependent because the other map, it's also infinitely long minimizer. So they all remember about the past. So they're correlated maps, but they're random maps. And the thing on large distances, if you take points far away from each other, they basically will be independent. But in I, they have dependence. And this is stationary dependence in time. And translation variant in x. Now, what I'm saying here is the following, that if you take average value, average derivative of this function f, and this is stationary in I, so I doesn't depend on I, it doesn't depend on x, that thing is equal to 1. Why is that so? Because if you take a long piece of your x space and take what is the image of this point will just have certain displacement order 1, and this point also have displacement order 1. So the image would have the length of the order of 2L, right? So, but the image of this thing, of this interval, minus LL, the length of this interval would be integral of the derivative of function f prime. And then if I divide it by 2 to the 2L, the initial length, that tends to 1. So that means that the average value of f prime must equal to 1. So g would have average derivative of g will have average value 0. 1 comes from here. That's trivial remark, but it has some consequences. Because when dimension 1, it would follow immediately that they have tendency that trajectories and the iteration of these maps would get exponentially close to each other. And that's very simple to see, because if you want to see, if you start to iterate these maps, so you take f minus 1, f minus 2, and so on, the derivative of the thing will be product of derivatives. From minus 1, so from minus n to minus 1, product of derivatives. And this became like e to the sum of the logarithms of f prime. And now you see that behavior of this is governed not by the average value of f prime, but the average value of logarithm of f prime. And if f prime has average value 1, then logarithm would have negative average value because of the inequality for the convex function. So you immediately see that average value of the logarithm of f prime is negative. And that's why points tend to get exponentially close to each other with the Lyapunov exponent given by this number, this negative number. That's fine. So points under dynamics, under iteration, get closer and closer to each other. But still, they cannot get very far away. Because again, if you take a piece from minus L to L and iterate it for a long time, the displacement of this point is governed by some kind of diffusion process. And displacement of this is also some diffusion process in N. So the image of length will be still order 2 to the 2L. It cannot be small, exponentially small with N. And the explanation of this is the following, that yes, points get together, but then there are separation points And a very short interval here is mapped in a long intervals here and there. And so you have combination of two scales, exponential contraction and this type of separation by the power law in T. And that's what we want to look at. Now, so since maps here are exponentially getting closer for most of the points, if I look what is the image, what is the map after certain long time n, I will see that it will be piecewise constant. Basically, you should think this is the whole interval maps at one point. And then another interval maps to this point, and so on. So the resulting map, effective map, will be piecewise constant map, but it will be monotone, piecewise smooth map, piecewise constant map. So we come to a problem that we iterate these piecewise constant maps of the type close, of the same type, x plus some displacement, which is stationary in I and homogeneous in x, and we iterate the thing, but the resulting map is piecewise constant. So what it means that it's piecewise constant, it means that the graph of this map is the following. And maybe I will use red here. So it would be some kind of staircase going around the diagonal. So that means that this interval maps to this point, next interval maps to this point, and so on. So that will be the graph of the function we iterate. That reflects the fact that things very exponentially get together here. By the way, if you're on a lattice, you can consider this problem on a lattice, not on a real space, then it would be exactly true that all points map to one point. And so now we come to a problem that we start to iterate this type of maps. And so the conjecture which we put forward here is the following, that universal property of the statistics of the resulting field of points when you iterate it for a long time is not related to optimization problem. It's related only to two facts, that things are monotone, basically monotonicity and the correlation on large distances and large times, that's the only thing which governs universal behavior. So basically we are claiming the following, that as long as the scale here is t to the alpha and alpha is fixed, there is only one statistics consistent with this information. So iteration by monotone maps, which are homogeneous in space and time, and which are resulted in certain behavior t to the alpha, where alpha can be any number, not necessarily two-thirds, results in a particular statistics of the point field, so these monotone maps resulting here. And so let me explain it, and then I'll present certain arguments why this should be true, right? So let me formulate, first of all, this conjecture in a little bit more precise form. Okay. So we iterate these maps Fix. We form x plus gix. Maybe it's even not at this point at the monotone. That's crucial. Homogeneous. Statistically homogeneous in x. And in t, stationary in I, in time. And then we iterate these maps. And suppose that iterates of this map, now let me I goes from 1 to n rather than from -1 to -n, it doesn't matter. So I iterate f1, f2, maybe -1, fn and -2, and so on, f1. And I assume that when I iterate point 0, they're all random. The image point 0, or any point, because it's homogeneous, will be distance of the order n to the alpha from the, in statistical sense, from the origin. So it means that variance will be n to the 2 alpha. I cannot determine this alpha. It can be any number. I don't want to consider numbers less than 1/2. 1/2 would correspond to independent choice of these maps. If they're independent, then displacement will be square root of n. But it can be more than that. Like here, it will be n to the 2/3. And then I'm claiming the following. The conjecture is that if I rescale this thing, so I consider fn minus 1, and I consider it in the coordinate x times n to the alpha, and take 1 over n to the alpha here, then it converges in distribution to particular random map. So it converges when n goes to infinity to a particular random map, piecewise constant map. So fixed point under this preservation, doesn't matter with what statistics you started, it will converge to particular fixed point, meaning that if you take this fixed point and apply this transformation to the point, it will not change. It will be the fixed point for this transformation. And this fixed point depends on parameter alpha, and basically doesn't depend on anything else. So for fixed alpha, this is a stable fixed point. Now, that's a rather strong conjecture. And so what are the arguments we have for that conjecture? So, well, one argument, it's a clearly randomization picture. So the thing can be looked at randomization of these maps after you iterate it for a long time. It's not necessarily that you even iterate it n time. You can iterate twice and so on and so forth. And conjecture said that under this randomization transformation, you converge to fixed point. Stable fixed point. This fixed point is stable. And the stability of this fixed point, under condition that alpha is fixed, explain extreme universality of KPZ statistical behavior in geometrical sense. So we can prove this statement when alpha is equal to 1/2. Alpha is equal to 1/2 corresponds to a situation where these maps are independent for different i's. And then we can prove that it converges to fixed point, and this fixed point can be described. Now, we also have numerical evidence that if we follow this procedure for maps appearing in context of random Hamilton-Jacobi equation, basically we were considering a setting of the last passage percolation, which is similar setting, then you get monotone maps with the same statistics coming from the problem of last passage percolation and from another problem, which has no connection to last passage percolation whatsoever. So the problem is the following. Maybe I have to say it now. It's coalescing Brownian motions. But this Brownian motion will be fractal Brownian motions. So what is the problem of coalescing Brownian motions? It's an object which was constructed in the 70s by Aratia and then appeared in many settings. So classical setting is the following. You start from independent Brownian motion from every point of a real line, normal Brownian motion. And then you say, when two Brownian motions meet, you continue with one Brownian motion. Now, you have to walk a little bit to prove that this process exists, because you have too many of these Brownian motions, and normally these properties are good with probability 1, but here you can continue them, but it can be done. So what Aratia proved is that although you started with continuum of these Brownian motions, after any time, positive time, say time 1, but it can be any positive time, it will be on the discrete set of points reached by these Brownian motions. So basically, Brownian motions from one interval would come to this point, and then from next interval to that point, and so on. So it will be piecewise constant map corresponding going from 0 to 1. And this piecewise constant map is, of course, a fixed point of this procedure. And you can prove that starting from any distribution of this type of maps, you converge to time one map for coalescent fractional Brownian motion, simple Brownian motions, and the rate of convergence is power law in n. That's a theory which we can prove. But that's an independent case. Now, this case corresponds to scaling alpha equal to 1/2. If you want to consider alpha greater than 1/2, you have to consider fractional Brownian motions. I don't know if everybody knows what is fractional Brownian motion. It's a process, it's a Gaussian process with stationary increments. But contrary to normal Brownian motion, these stationary increments are not independent. So they're dependent Gaussian random variables, and if you take some of them, they behave like not square root of n, but n to some power. This power is called, this exponent is called Hurst index. So it just, if you put enough correlation between increments, then displacement will be n to any power between 1/2 and 1. Actually between 0 and 1, but there is a difference between Hurst exponent, it's called Hurst exponent h, can be between 0 and 1/2, then h is equal to 1/2 is just normal Brownian motion, and h greater than 1/2, it's a case which we consider here. And we work in this situation because in this situation there is a positive correlation between increments, and this situation is negative correlation between increments, so we're not considering it. So we considered fractional Brownian motions with exponent h equal to 2/3, because that would mean that displacement will be order n to the 2/3. And we construct point field, or say monotone maps corresponding to this situation, and statistics which we see for fractional Brownian motion is the same as for, well, it's not the same, it's the same numerically, so we do test Kolmogorov-Smirnov test, we see that this is very similar statistics of monotone map appearing for fractional Brownian motions and for the last passage percolation. Last passage percolation, of course, belongs to the KPZ universality class. This process of coalescent fractional Brownian motion has nothing to do with KPZ universality class traditionally, but it carries the property of monotonicity. So that's a thing which we believe is correct, and we numerically see some evidence of it. Now, I want to say that when I said coalescing fractional Brownian motion is not as innocent as for normal Brownian motions. You see, when they collide and you want to consider them as one thing, for Brownian motion, it's independent. The continuation is dependent of the past. But for for fractional Brownian motion, it depends on the past. So you have to choose how you want to continue. And we considered several possibilities of continuing. Basically, one of them, if two things meet, you just flip a coin and decide which one you continue with. It's one way. Another way can be just to continue as independent Brownian paths, fractional Brownian paths, and other situations we also considered. And in all the situations, we saw that statistics of the monotone maps was very similar by Kolmogorov-Smirnov criteria. It was undistinguishable from the last passage percolation. So, so what we are proposing here is a little bit different view of the problem of universality. So it starts with geometrical object. Geometrical object is a point fields corresponding to monotone maps. And we believe that they just monotonicity and nothing more, plus the correlation, determine statistics, unique way. So there is a one parameter family of fixed points and statistics of these monotone maps, which is completely characterized by parameter alpha. In particular, for alpha equal to 1/3, that corresponds to KPZ. So geometrical properties are the same. Now, in KPZ, you have to do more than that. You also want to look at the airy processes, so say get Tracy-Widom distribution. So you also want to see what is universality, not of geometrical object, how geodesic look like, but what are the lengths of these geodesics, or what is the statistics of interface. And then I don't know much about that, but that's a question which you can study. It's the following question. So I'm kind of trying to describe what may be the strategy of proving universality if the conjecture is proved to be correct, which is far from true at the moment. It's just numerical evidence for other constant. But suppose it's correct, then the next question will be the following. So there is an airy process, or sometimes called kind of two-parameter airy process, x and y, has the following meaning. In rescaled coordinate x and y, it says the following. It's already rescaled, so it's a long time interval t. Things are rescaled by t to the 2/3. And so what is described here, it's a stationary process in x and y, translation variant in both coordinates. You just characterize the optimal action connecting to point x and y. Now, real points will be x to the, so we will think this is t, large t, but rescaled t will be 1, and real x to the 2/3 times this x, to the 2/3 times this y. And the thing is an action, optimal action between x and y. You subtract some constant depending on t, you divide by t to the 1/3. There are some constants which I'm not writing here. And you also compensate by x minus y squared. And then you get this airy process xy. So you take optimal action, you normalize it by KPZ normalization, you compensate for the fact that they can be far away, and that is stationary process A to xy, which was recently constructed in some integrable models by Balint-Virag and in his students. And so the problem is the following, that if you know this airy process, airy xy, then you can study the following problem. The map between x and y, you define a map, y on x. So what will be the y on x? It's a minimum over all y, x is fixed, airy xy, plus x minus y squared, which we subtracted here, plus, and here I would put Wiener process on y, which is independent from this area. This Wiener process of y corresponds to the fact that that is accumulated action from minus infinity to that time. This will be Wiener process on y. So that is a map, transport map, corresponding to situation described if airy process is described. And so suppose I know statistics of this map, which I said it's completely determined by alpha, and alpha is 2/3. Then the question, how many choices of this stationary process you can have consistent with the given statistics of a map? And perhaps there are not many choices. Perhaps the statistics of this map, f on x, roughly describe the statistics of process here in a unique way. So there is a unique airy process which is consistent with the transport properties. And you should not be surprised when I say this minimum that you get piecewise constant map, because actually airy process is very wiggly and it's not a smooth function on x and y at all. So normally you would think that the minimum y on x will depend kind of continuously on x. But here it will not be the case. What will happen here, that the whole interval of x will come to one point, and then another interval of x come to another point, and so on. So you again would get piecewise constant map. And I'm saying that probably, well, it's possible, I don't know exactly, but maybe there is not so many choices of stationary map, of stationary process, airy xy, such that what you get here is prescribed by the fixed point equation. And that may be the way to kind of handle universality. But also what I'm saying is that universality seems to be, in geometrical objects, it seems to be much wider, much broader than universality in traditional KPZ, because the only thing we're using here is monotonicity. So basically, in one-dimensional space is so little space that there is not much freedom for you to choose statistics consistent with these dynamics, with stationarity in X and stationarity in Y, in I. And that's the point we are making, and we have numerical evidence that it might be correct. So I guess I can stop here.
Thank you very much. Are there questions?
Yes.
So this formula you wrote down there, this is sort of the fixed point for alpha is 2/3 then, or that's a formula for the fixed point?
Yeah, this
map.
would be statistics corresponding to 2/3, yes.
Okay, so do you think there's a similar formula for other alpha with other?
That's a very good question. For other alpha, I don't know candidate for every process and for whether there is a height function corresponding to other alphas. So far, we know that there is 1/2 is a special case, and it's integrable case, actually, in many respects. 2/3 is also integrable case in many respects. So I would doubt that other alphas are integrable, but it's a good question whether you can construct something corresponding to this point fields in other processes. But it's conceivable, it's possible. I just don't think it will have as nice properties.
So formula then for alpha half, or?
I don't know it. Yeah, it's a good question, yeah. 1/2 would be the first candidate to look at it, yeah. Okay, so what I'm saying, the relation is the following, that whenever you have monotone process, random monotone process, which has displacement order time to the 2/3, it would have the same statistical properties for the concentration points. And that's it. Fractional Brownian motion with Hertz exponent 2/3 is a process which we know would have displacement to 2/3, time to the 2/3. But basically, we're saying that if you invent any process which is random in time and random in space, which has displacements order t to the alpha, they will have the same statistics.
So there is no formal relation.
There is no relation. It is much broader context than normal KPZ relation. That's one of the points, that you don't need KPZ for that. You don't need optimization for that. You just need displacement of prescribed order. Yes.
Brownian motion case, the statistics of coalescing and annihilating Brownian motions are kind of the same. Right?
Of coalescing and annihilating. I don't know. I mean, why should we? Annihilating, they just disappear, right? I mean.
Yes, but when you start the same way that Karagi.
Maybe you're right. I never thought about it.
There's some work of people in the UK, Roger Tribe, and Oleg Zabrowski.
Yeah, they looked at coalescent and Brownian motions and correlation functions for that. But it was several people who looked at this as well. So you can describe for coalescent Brownian motions, when you get this statistics of the monotone map, which correspond basically to statistics of this point field and that point field, you can describe correlation function precisely. So it's integrable model. There is certain way to describe it through the calculating certain determinants. But it's probably, I don't know whether the same can be done in even for 2/3. But that's how much of these correlation functions are integrable. People didn't look very much on the statistics of these concentration points. They were mostly all mostly exact formula for the optimal action for function for this process area and this type of things, but not for geometrical objects.
Further questions? Well, if not, then let's thank Konstantin again.